Hello everyone. So in the last lecture we discussed about shock waves, that is Rankine-Hugenoid treatment of shock waves, and we have the Rankine-Hugenoid equations. So today we will discuss a little bit more about Rankine-Hugenoid equation or Hugenoid curve, and then we'll discuss about shock wave generation from impact. So what we discussed in the last class, from the conservation of energy, we had this equation E minus E naught, that is the internal energy, half of P plus P naught multiplied by V naught V, which is P is the pressure of initial and final configuration, and V is the volume. So this is, we talked about Rankine Hugenoid equation. So this is basically a relation say between P pressure and density. So we will have the graphical form of this equation or the Hugenoid curve. So here we have the pressure on the y-axis and the specific volume on the x-axis, which is 1 by rho, 1 by mass density. So the Hugenoid curve will look something like this. This is the Hugenoid curve. This is Hugenoid curve from the Rankine-Hugenoid equation. Probably I will redraw it. Okay. So now this Hugenoid curve is the locus of all shocked states of the material. So this is essentially describes the material properties So relation between P and density, pressure and density. However, this curve has some discontinuity, as can be seen from this Rankine-Hugenoid equation. So that is why it is difficult to find the pressure density relationship from the Hugenoid curve, and then we use another line, a Rayleigh line, is a straight line. This is a straight line. This is called Rayleigh line, and suppose this, at this point the pressure is P1. So this Rayleigh line is intersecting the Hugenoid curve at this point, and that is corresponding to pressure P1. So Rayleigh line gives the shocked state of at pressure P. Sorry, this is not P, this is P1. So at pressure P1, so the Rayleigh line will give us the shock state, so that we can determine the other shock wave parameters. So what we need to know from here is we want to have the slope of the curve, slope of the Rayleigh line. So what we can do is, this is the pressure P1, and then pressure P naught is let us say is the reference line, and then we have the volume, the specific volume V1 here, and then V naught. So the slope of this line will be P1 minus P naught divided by V1 minus V naught. So we will try to find this slope so that we can determine the shocked state at a different point, at other points. So how to do that? From the conservation of momentum, so we have P minus P naught is equal to rho naught US UP. That is what we discussed earlier. So from here what we can get is P minus P naught divided by UP is equal to rho naught US. Again, if we use conservation of mass, rho naught US, rho naught is the, so if I again draw this, just if you do not remember, so this is our shock wave discussed in the last class, shock wave with velocity US. So behind the shock front, so this density is rho and pressure is P, and the head of the shock front, this is density is rho naught and pressure is P naught, and then UP are the UP is the particle velocity. So rho naught US is equal to rho naught US minus UP, and this will give us an expression of UP, which is US rho minus rho naught divided by rho. And if we replace substitute UP in A, substituting UP in A, we will found that P minus P naught divided by rho minus rho naught by rho, and we have that US. So that US we can keep it at the right hand side. So that will give us US square, that is the velocity of the shock wave, and which will be, again we can write in this way, P minus P naught 1 minus rho naught by rho. Under left hand side expression we can write it this way, and but we know that this rho naught divided by rho is nothing but V by V naught, the ratio of the velocities, volumes, ratio of the volumes. So so using that relation, if we can write it like this, and this will be again we can express it in this form, which is equivalent to P minus P naught divided by V minus V naught, and that is, we are writing the opposite, that is why the minus sign will come here, rho naught US square, but the another rho naught will come from this V naught, will be is equal to rho naught. So that will give us rho naught square here. So this is the slope of that Rayleigh line. So we will go back to that slide. So what we got, this the slope of the Rayleigh line, which will actually can determine that this continuity we found in the Hugenoid curve. So that will be rho naught US square. So from the Rayleigh line, so we can find out the shock state. If we increase P, the pressure, that will increase the slope of Rayleigh line, and also it will increase the velocity of shock wave. And again we can have another plot PUP plot. So this plot is pressure versus particle velocity. So pressure versus particle velocity from conservation of momentum, P minus P naught divided by UP will give us rho naught US. So this will give us this type of curve. So we have seen that pressure versus specific volume and pressure versus UP, that is the particle velocity. So these are the different curves or relationship between the shock wave parameters. So next we will discuss about producing shock waves, generating shock waves with impact. So we will consider the simplest case of impact, very simple case of shock wave generation. So this impact will be have three characteristics. First one is this should be planar, and the second, it should be a parallel impact, and third, it should be normal. So these are the conditions for the simple shock wave generation. So planar means it's impact of two flat surfaces. We will dot a diagram here. So first maybe so we have this projectile and this is the target. And target. So this is the projectile hitting the target. So we have two flat surfaces. So this is a planar impact, and it is parallel. Parallel plate will ensure that all the points of the two surfaces contact at the same time. At the same time. So we have all the points. So here we have in the projectile we have all the points, and here we have in the target. So all the points in the two surfaces will at the same time. So it should be exactly parallel to each other, and the normal means the direction of projectile, direction of projectile movement is perpendicular to its surface. So the projectile surface is this one. So its direction of movement is perpendicular. This is the surface of itself. I mean, that's not the target surface, but this is should be projectile surface. We'll again discuss this problem in details. So let's assume that we will draw a line first. So first case is so we have the target here. I need to make this some, let's say, rectangular block. In 2D we are seeing. So this is the target, and our projectile is something like this. So projectile is coming at a velocity v. So this is at rest, its velocity is 0, this is at rest. So now it will have an impact at the time of impact. At the time of impact, so this is the impact surface. So we can call this is t equal to 0, and t is actually before impact, we can call that, and this is, we can write that the point of impact. This is at the just the impact point, the second case, and the third case is this is during impact, which is t is greater than 0. So impact is still happening, and the projectile will go little deeper from that reference line, and this is our target. We can see here the impact velocity is the same as v, what we see in the left hand side figure. So this is impact velocity, v is the impact velocity, and this is the impact interface. We call it the impact plane or impact interface. Interface we are saying because it is the interface between the target and the projectile. And now in this case, during the deformation process, so we will see that there are two waves, shock waves generated on the both side, projectile and both projectile and the target side. So these are the compressed region. So this one and this one, they are compressed region, compressed region of target and the projectile. The velocity of the wave, shock wave, this is actually the compressed region, that means the shock wave front is this boundary. So us1 is the velocity of the shock wave, and as we can understand, this portion and this portion are uncompressed, and this is this portion is still at rest, this portion, and this portion is still moving at velocity v. But if you take a particle velocity, we will call this as up1 of the compressed region, and similarly, okay, I did not do the other one. So this shock wave, the one is as we discussed that this is going upward, which is shock wave of the projectile. So, I will write it here. This is the projectile and this is the target. So, the one is going upward, that is shock wave generated in the projectile, and one is going downward, that is shock wave produced in the target. We will write the velocity as u subscript s2. So, 2 for target, 1 for projectile. Similarly, for particle velocity up1 for projectile and up2 for target material. We need to have two conditions here. So, two conditions of this impact, so that for the prediction of pressure P, and then subsequent we can even predict the particle velocity. So, these two conditions are, first one is the material has to be continuous, has to be continuous, that means continuous across the impact interface. Impact interface. So, this side and this side. So, this should be continuous. Continuous means the impact particle velocities are same. It means particle velocities are same, and otherwise what happens? Otherwise we may get some voids or high density region. So, that I think we can understand that if the particles are not traveling in the same velocity, there will be some voids or there will be some very high density regions, that means higher than the density of the original materials. So, that can generate. So, this is condition number 1, and the condition number 2 is pressure has to be same in the both of them, P1 equal to P2 in the compressed region. So, P1 and the projectile should be equal to P2 in the target. So, otherwise there can be we can imagine that there can be another pulse, another wave. So, if the pressures are not same, we cannot assume it to be the same wave. So, that the pressure difference can create another pulse. So, these are the conditions we will follow when we will derive the relations. I mean, we want to determine the pressure of this shock waves of the simple case of shock wave generation under impact, and also we will get the particle velocities. So, now in this case the interesting point here is to to establish the particle velocities, the condition 1, we told that the particle velocities are same. So, here we showed that we have a particle velocity up1 and we have a particle velocity here which is up2. So, the particle velocities are same. To show that we need to take a fixed reference frame. Suppose this fixed reference frame means this is the observer, this is our observer. So, if it is a fixed observer outside of that, that can see that the particle velocity in the original material before the impact, or the part of the material which is uncompressed is still v1. That means the particle velocity UP is v for uncompressed region, and then particle velocity for the compressed region, if you think this will be reduced v minus UP1. So, UP1 is the, so UP1, so actually if you see v minus UP1 is the particle velocity when we have a fixed observer, and this particle velocity is actually UP1 for the projectile if that is a moving reference. So, moving reference, let us say this moving reference, if we take it as impact interface, So, if it is the reference is the impact interface that is moving in this direction, so then the particle velocity is UP1, and if we take a fixed observer outside the system, that is projectile target system. So, in this case, if you you know that this target is the lower one, target system, the target projectile target system. So, then our particle velocity will be v minus UP1. So, and this will give us our condition, the particle velocity is the same. That condition means that this in the projectile, that means particle velocity, I will write PV of projectile is equal to particle velocity PV of in the target, or you can simply write even U subscript P for PV. So, this will give us V minus UP1 is equal to UP2, which is the particle velocity in the target. So, this is will give us UP1 plus UP2 is equal to V, which is the impact velocity. V is the impact velocity. So, to determine the pressure, so basically our goal is to determine the pressure and also the particle velocity subsequently. So, to determine the pressure, so we will first, let us say we will use conservation of momentum. Conservation of momentum, that is nothing but the final that is the impulse is P2 minus 0 A dt. P2 is the pressure which increases from 0 to P2 multiplied by area, that will give us the force multiplied by dt, that is the impulse, and for the change in momentum is rho naught to, let us say, us to a dt. This one is the volume, and the entire including rho naught, this is the mass, multiplied by change in the velocities of the particles. So, this is the mass of that compressed region. So, ultimately we will get a relationship like P2 equal to this is for the target we are talking about, this is for the target material. So, P2 equal to rho naught subscript rho naught 2 actually, and then US to UP2. Similarly, for the projectile, we can have P1 is equal to rho naught 1 US1 UP1. So, this is again from 0 to P1 pressure, and then the particle velocity are from initial V to V minus UP1. So, this will give us this. So, pressure in the projectile, pressure in the target. So, these are from conservation of momentum, and also the equation of state that we discussed in the last lecture. The equation of state for the two materials means the materials of the target and the materials of the projectile. So, we have two relationship here, US1 C1 plus S1. So, as you know, this is equation of state is the relationship between the shock wave velocity and the particle velocity, and C1 and S1 are two empirical parameters. So, similarly for target, this is C2 plus S2, these are material parameters, S2 multiplied by UP2. So, if you substitute these equations, substitute these EOS into these two equations, let us say I will write A and B. If we substitute the EOS in A and B, so from A and B, so what we will have is for the projectile P1 is equal to rho naught 1 C1 plus S1 UP1 multiplied by UP1, that you can understand. This one is we got it from the EOS of the projectile material, and then this will give you rho naught 1 C1 UP1 plus rho naught 1 S1 UP1 square. Similarly, for the target P2 is equal to rho naught 2 C2 S2 UP2 UP2. So, now we will set the condition P1 equal to P2, which is our condition number 2. So, what we will do is we will replace UP1 in this equation. So, that will give actually that we know from earlier, this UP1 is V minus up2. So that means here we have the transformation of axes, a transformation of axis, that means our reference frame is now, as we know, that is the fixed observer outside of the system. So if we substitute this relationship in, let's say we have D and E. So in D, let's say from D, so what we will get is P1 rho naught C1 V minus UP2 plus rho naught 1 S V minus UP2 whole thing square. Then we have this condition P1 and P2. So what we will do is from E and F, okay, so from E and F, and if we are using P1 equal to P2, so we will do in the next slide. So this will give us from E and F, I will write it again, from E and F, and as we know P1 equal to P2, so probably we can here write it again, P1 equal to P2. So that will give us rho naught 1 C1 V minus UP2 plus rho naught 1 S1 V minus UP2 square is equal to rho naught 2 C2 UP2 plus rho naught 2 S2 UP square. So this will, we can rearrange, I am just omitting few of the steps, and we can rearrange and can get rho naught 2 S2 minus rho naught 1 S1 UP2 square plus rho naught 2 C2 plus rho naught 1 C1 plus twice rho naught 1 S1 V UP minus rho naught 1 C1 V plus S1 V square is equal to 0. So this is as you can understand, we are having a quadratic expression in terms of UP2, and this is nothing but your like ax square plus bx plus c equal to 0, and we know that the root of this equation will be equal to x equal to minus b plus minus b square minus 4ac square root of the whole thing and divided by twice a. So here in this case, as we know, a equal to rho naught 2 s2 minus rho naught 1 s1, b is equal to rho naught 2 c2 plus rho naught 1 c1 plus twice rho naught 1 s1 v, and c is equal to minus rho naught 1 c1 v plus s1 v square. So if you want to get the this expression, so up2 will be a somewhat a long expression. So probably I don't want to write it here, so you can see that. So what will happen is this you can replace this ABC in this equation, and so this will give you twice a, 2 into a, from UP we can even get the expression for pressure. So if the target and projectile material the same, target and projectile material are same, so what will happen then, rho naught 1 rho naught 2 is equal to rho, similarly C1 C2 equal to C, and S1 S2 equal to S. What will happen in this case? So if you see the other expression, though we have the A will be equal to 0 for same material. So if A is equal to 0, then we are left with only Bx plus C equal to 0, and this will give you x equal to minus C by B, right. So minus C, and then which will be nothing but UP equal to actually rho CV plus SV square divided by rho twice C plus twice SV. So this will be rho will be cancelled out, here V C plus SV divided by twice of C plus SV. So this will cancel out, and finally this UP we get it as V by 2. So basically the particle velocity will be V by 2. So that means if the materials are same, particle velocity is will be half of impact velocity. So this will be half of impact velocity. Yeah, so that's all for today. So we will be discussing a little bit more about it, the graphical solution of this whatever we discussed today, and then we will discuss about the methods of getting the equation of state of shock waves. So this is all for today. Thank you.